Today we'll be looking at a number of concepts in terraforming, the field which looks at how to make other worlds more hospitable to humans and other Earth life by making those worlds more Earth-like. If you're a subscriber to the channel, you probably know the videos on the channel fall into two basic categories, the long ones and the incredibly long ones. This one is going to be of the second type, because it is a long subject. So now probably would be a good time to go grab a drink and a snack. Also, if you're not a subscriber to the channel, you can become one by just clicking the subscribe button in the lower right corner. And while you're down there, you probably want to turn on the closed captions for the video. I can be a bit hard to understand even when I'm not spouting technical terms, and we will have a lot of those in this video. Since this is a summary video, I will be including both some links to other sources expanding on this subject in the video description, as well as referencing some other videos by myself and others. These will usually appear as a thumbnail with a yellow box around them. Most will appear again at the end of the video, but you can click on these at any time, and it should just pause the video and open that other one in a new window. Just as an example, while we'll talk about Mars a great deal in this video, it's not our real focus, and if you're interested in the nuts and bolts of getting to Mars and starting terraforming with only modern technology, then Sean Moss's The International Mars Research Station is definitely a good place to get started. And the attached video of his TED Talk is a great introduction to getting to Mars. Another person I'll be referencing a lot is Martin J. Fogg, and if there's anyone who knows more about terraforming than him, I haven't met them. A link to his website on terraforming is below in the video description, and he literally wrote the book on the subject. We also all tend to hang around the same online forums discussing these kinds of subjects, so while I always try to answer any questions you have in the comments section, you may want to give those a try too. They tend to be very friendly stomping grounds for scientists, science fiction writers, hobbyists, and people just curious about the ideas. So one of the first things we need to discuss is, what is terraforming? Well, the word is plain enough, terraforming, terra, Latin for earth, or earth forming. Historically, it first popped up in a short story by Jack Williamson called Collision Orbit, back in Outstanding Fiction in 1942. This was the same story that saw the first use of antimatter in science fiction. Williamson also coined the term genetic engineering, and probably tops the list of greatest and most influential science fiction writers most people have sadly never heard of. In his story, the example of terraforming is an asteroid just over a mile across with an artificial gravity field in it. So originally it wasn't a planet, or even a large asteroid or moon. I stress that because making a planet like Earth tends to be the concept and image most think with terraforming, but it's not limited to planets, and it hasn't been since day one. Genetic engineering is also of interest to us because there's an alternate approach to terraforming, or one used in tandem with it, sometimes called bioforming. And that's where you aren't changing the world to be more Earth-like to support Earth life, but changing Earth organisms to be able to live on an alien planet. Terraforming and bioforming are two sides of the same coin in some respects, and often assumed to be used together. Still, you often have people very opposed to terraforming for wrecking an alien environment, inhabited or lifeless, or opposed to bioforming because it involves genetic engineering. This isn't an ethics class though, and it also isn't one on bioforming, nor am I qualified to talk about it in real detail because I'm not a biologist, so we won't be discussing it in detail. Another term in common usage is planetary engineering, a fairly straightforward term, and in many ways better than terraforming since it's maybe a bit more on the nose. You are engineering planets for habitability by Earth life more than you're trying to make a planet a close copy of Earth. You also occasionally hear the term para-terraforming, and this usually means just building domes on a planet. If taken to the extreme so that the entire planet is domed under, we call this a world house, essentially a world-spanning greenhouse. Also, para-terraforming is often used to reference the first steps in most terraforming processes, where you're setting up a small living area like domes on Mars or floating cloud habitats on Venus to live in while you're making the planet more livable. If you've seen my original megastructures video or any of the follow-ups discussing rotating habitats, those are sometimes considered para-terraforming examples too, especially if embedded in something like an asteroid. They replicate the conditions on Earth much more closely than you could plausibly get on Mars, for instance, because you can tailor them to whatever you want. Want is the key word there because not everyone can still certain differences between Earth and another world as important to fix. They might not care, for instance, if the gravity is a bit heavier or the day is 30 hours long. With rotating habitats, you're pretty much able to tailor everything. But even though the original example of terraforming in fiction was a small asteroid, building giant cylinder habitats inside asteroids normally isn't considered terraforming, so we'll look at those more properly in the megastructures videos. So terraforming itself is a pretty simple concept: make a place more like Earth. But which factors are most important? In which ones is a close approximation to Earth okay? To a degree, it's a eye of the beholder, your mileage may vary kind of thing, especially when it comes to setting which differences are priorities and how close to Earth is close enough. So what are the big differences that need to be changed to make a world like Earth? We're not focused on Mars or Venus, but let's take a look at some of the key differences both have with Earth in this chart. In some ways, it's a very Goldilocks case. Not too hot, not too cold, too much air, too little air, but for neither is it where we can really breathe. You need to make them warmer or colder. So how do we do that? You need to add breathable air and remove unbreathable air. How do we do that? Venus's gravity is just about right, Mars has a day length that's just about right, but gravity is too low on Mars and Venus's day length is almost a year long. Can we change those? Can we even change things like gravity, or year length, or a planet's axial tilt? The simple answer is that any planet, any moon, any asteroid can be made very like Earth in most ways. How close depends on what quality we're talking about, what tools we have, how much of those tools we have, and how stubbornly persistent we are at that goal. Even the most basic terraforming takes centuries, and must take centuries, as we'll see, even if you got something really neat like near-limitless energy or self-replicating robots. The good news is humanity has an impressive track record of being stubborn, and has been known to spend whole centuries working on projects. From the pyramids and the cathedrals to highway systems, canals, and walls, we have shown a willingness to dedicate massive resources and long-term efforts to getting projects done. And we did most of those back when people lived about half as long as we do now, and with far less excess wealth to devote to them. People often wonder if we'd be willing to devote centuries to projects like terraforming, and for my part, though I often get accused of excessive optimism, I think the answer is a clear yes. So let's start by talking about those three most basic qualities a planet needs to have: the right temperature for life, the right atmosphere for life, and water. Water is actually quite easy, on the surface anyway. It's one of the most common molecules in the universe because its constituents, hydrogen and oxygen, are the first and third most common elements in the universe, and it's a very simple molecule to form. Ironically, in most cases it's coming up with the hydrogen, the most plentiful substance in the universe, and not the oxygen, which is the problem. Hydrogen tends to be a touch rare on rocky planets, as is helium, the second most common atom. The reason for this is simple enough. Planets we are interested in are hot, and are regularly hit by ionizing radiation, asteroids, and other items that tend to help evaporate the atmosphere into space. I've mentioned in the past that people tend to mistakenly assume places like Mars and our own moon have too little gravity to hold atmospheres, and we'll talk about that briefly in a little bit, but the key thing is the various means by which matter escapes from atmospheres, regardless of the various physical mechanisms being used, relies very heavily on the mass of the molecule. Hydrogen and helium molecules are quite light and fly away quite easily. Hydrogen, unlike helium, can bind to other heavier atoms to form heavy molecules, so even though it's lighter as an atom than helium, it often remains in larger quantities. Still, it will often find itself free from molecular bondage to heavier kindred, either paired up with another hydrogen atom or kicked free entirely by radiation in the upper atmosphere, and can then be sent shooting off into space much more easily than things like oxygen. Oxygen, being heavier, stays around, but actually disappears from atmospheres in the other direction by getting sequestered into rock. Most rocks, be it sand or limestone or granite or metal ores, tend to be composed in large part of oxygen. If there's not a lot of water or ice already on a planet, you can always get more oxygen by taking it out of those rocks. That's quite energy intensive. It's so energy intensive that even if you covered every inch of the planet with efficient solar panels that did nothing but cook oxygen out of the rock by melting or by electrolysis, it would still take anywhere from many centuries to many thousands of years to collect all the oxygen you need for even modest shallow oceans and breathing air. Of course, you also have to worry about keeping that oxygen. If removed from the dirt, it might just go right back in. Separate iron oxide, rust, into iron and oxygen, and the iron will just start rusting again and sucking the oxygen back into itself. Still, you can get oxygen out of it to make air and water. But you'll still need hydrogen for water, and odds are you'll need to bring it in from elsewhere. If the planet had large quantities, it would already have oceans. Now, you could opt to just bring in water directly, as it is plentiful in the form of ice in the outer solar system, and likely would be in any solar system. But it's debatable if this is much of a cost-saving exercise, since most of the weight of water is oxygen, nearly 90% of the mass. And moving that oxygen millions of miles costs energy in similar ranges to cooking the oxygen out of the rock. It also matters where you're getting that energy from. Planets we're interested in terraforming tend to be good places for solar power. Places where ice is plentiful are obviously not. If they got a lot of sunlight, they wouldn't have ice. The flip side is there are places in the solar system where hydrogen exists in massive quantities by itself, instead of as water or methane or ammonia, but these tend to have massive gravity wells. Gravity is never your friend when you're trying to ship matter in bulk. We'll talk about moving hydrogen when we talk about moving air, since it's a similar process for getting nitrogen, another thing not in much supply on Mars, for instance. Before we move on to that, though, we have two other big concerns that often get overlooked in terraforming where water is concerned. First, while Mars, for instance, isn't a great example because its crust is both similar in composition to Earth's and has previously had water on it, we need to remember that water dissolves stuff, like continents. The rate water evaporates at, and therefore rains at, isn't too well related to the amount of it now on a planet in your early terraforming days. Long before you've got swaths of ocean miles deep, you'll have rainfall. Lots of rainfall. Because a thin puddle of water a few inches deep evaporates water just as fast as a deep trench with the same surface area. So long before the planet has anything like the volume of water Earth has, you'll start getting serious amounts of rain. Especially if there's not much atmosphere, because water evaporates quicker in lower pressures. Now, lots of rain is good, except rain dissolves dirt, and there won't be any plant roots helping prevent erosion since plants need rain. And without pre-existing rivers, you'll end up with floods and buildings destroyed by waves of mud. So terraforming requires you either get an atmosphere in place before there's much water, or requires you go out cutting spillways and reservoirs all over the place. If you know the kind of engineering muscle it takes to keep the Mississippi River in check, or to prevent soil erosion of farmland, think of that and multiply it by 1,000. The other issue is you don't just want to keep toxic heavy metals out of your soil and water, but you also need to make sure some other things are dissolving into it, like salt if you want seawater. Earth's crust has a lot of sodium in it, 2 to 3%, similar to the salinity of our oceans. Sodium and chloride, though not terribly rare, aren't going to be very abundant on every planet's crust, and aren't particularly common in asteroids either. So water, which initially seems simple, turns out to be a lot more complex than we first thought. How about air? We've already mentioned one way to get air, baking it from the rocks, or electrolyzing it from the water if that's very abundant. But that's just oxygen. We need nitrogen too, for plants to live. Now on both Venus and Mars, nitrogen is the second most abundant component of air, right after carbon dioxide. But for Mars the atmosphere is quite thin, so that doesn't really equal much, only a small fraction of what is needed. And it doesn't appear to have it in abundance in the rocks either. If we're wrong on that, and we may well be, then we can cook it out of the local rock. In Venus's case, we have the reverse problem. Venus may only have 3 or 4% nitrogen compared to Earth's own nearly 80%, but Venus's atmosphere is nearly 100 times more massive than our own, and Venus is a bit smaller than us too. So it has a few times more nitrogen in its air than we need for an Earth-like atmosphere there. Now, you need some more for in the dirt and plant themselves, but not much. So Venus is one place we can get nitrogen from Mars at. The other is Saturn's moon Titan, which has an atmosphere composed of almost pure nitrogen. And the rest is mostly methane, which is quite handy itself for terraforming cold worlds like Mars, because it's a greenhouse gas and has a lot of hydrogen in it too. How do we move air from one place to another? How do we move hydrogen from a place like Jupiter to Mars or Venus, which itself has very little hydrogen? Just imagining a giant ship moving billions of tons from place to place is probably a bit unrealistic. 1,000,000 tons of air at normal pressure takes up about a cubic kilometer, and even a ship that big would need to make a few billion trips to move a planet's atmosphere. The biggest oil supertankers on Earth can haul a few 100,000 tons of oil, and you're thinking of things that are that big, making the round trip once a year for 1,000 years, you need 10 million of them in service. Even when we're talking about redirecting comets to the planet, we're talking about needing hundreds of millions, if not billions of them. If you've seen any of the megastructures video on this channel, you might be thinking of a few solutions already. The first 3 episodes of that deal with nothing but moving huge amounts of matter off planets cheaply. And it needs to be cheap. For context, if it were costing only $1 per ton, you'd still spend over $2 quadrillion, which is more than our entire planet's GDP for a decade. Don't have many illusions about terraforming. People often talk about how we can do something, then just sort of hand-wave how that goes from in the lab to being done on a planetary scale. With the exception of paleoterraforming, and that's one of the reasons why it's so popular, there's not a single planet we could terraform without having massively improved automation and power sources. Sometimes I'll mention heating planets with orbital mirrors the size of planets themselves, or rather mini mirrors with the total size on that scale, and people will object on the grounds that doing something like that would be ludicrously expensive. Then they'll turn right around and suggest moving a planet's worth of air and water. Those planet-sized orbital mirrors will be thin sheets a few millimeters in thickness tops, so a planet-sized one would not even mass 1 trillion tons, whereas Earth's atmosphere weighs about 5,000 trillion tons. Now, that doesn't mean it can't be done. The resources needed are in the solar system. Jupiter has many times more hydrogen than Earth has rock. Titan and Venus both have abundant nitrogen, and oxygen is plentiful everywhere in the inner solar system except on Mercury. On a place like Titan, we'd likely go the mass driver route, filling metal pods about as thick as a soda can and as big as semi-trailers full of high-pressure gas and just firing them off, one after another, from the surface. Titan's gravity is so weak compared to Earth that we can build structures miles long and high, peeking out over the atmosphere. Coming up with a metal for the structures and pods isn't too hard either. Titan has a rocky metallic core, and digging very deeply on low-gravity worlds is actually quite easy, especially when you're mostly just melting your way through ice until you get to the rock. And Saturn has other more rocky moons that could be used as sources too. Mass drivers are perfect for a place like Titan, as are space elevators, except that Titan doesn't get much sunlight for solar power, only about 1% of what Earth gets per unit area, and it isn't likely to be abundant in fissile materials like uranium either. So Titan is only a good source for nitrogen if you've got nuclear fusion. Without that, you might still be able to run mass drivers. Solar can be concentrated with thin mirrors and lenses, for instance, but it wouldn't be easy, and we're talking about shifting trillions of tons of matter to another planet every year just to get enough to finish the job in a timeline of centuries. If we're imagining those pods, say containing 10 tons of nitrogen gas, you'd have to launch one every second for 30 million years just to get to the right amount of nitrogen for Mars. That means needing a lot of mass drivers and a lot of energy to get it done on any timeline worth doing, and the entire solar energy budget of Titan, if we wrap the thing in solar panels, is only around 1 billion megawatts, compared to Earth's own 200 billion megawatts. Even with very efficient conversion of that light straight into kinetic energy, you need several thousand megawatts per ton of matter flow you're trying to get off into space and off to Mars, and that level of efficiency is just not too realistic. But if you achieve that, you could move enough nitrogen to Mars in several centuries to get the job done. Low efficiency, longer timelines, more panels and mirrors, all needing maintenance and needing it for longer. Needless to say, nuclear fusion makes things much easier if you've got it. And it makes terraforming Titan much more plausible too, which you might want to do too if you're planning to hang out there for centuries pumping gas off anyway. For Venus and Jupiter, the game's a bit different. You could put floating mass drivers in the upper atmosphere, shooting nitrogen and carbon dioxide off Venus and hydrogen from Jupiter. But for Jupiter, you have the advantage that it's got a very strong magnetic field. And if you've seen the video on skyhooks, you know that that's ideally how you operate a skyhook, by regenerating their momentum by using electricity to shove off the planet's own magnetosphere. This is a process called electrodynamic tethering. So they can rotate down, drop off empty pods at floating refineries, pick up full ones, fling them off to their destination, and end a little lower in the process from friction and momentum transfer. They then shove off the magnetosphere to get back up. Hypothetically, you could mine Jupiter's moons for the metal for the pods, fling them to Venus, which catches them, steals momentum in the process, empties their hydrogen into Venus's atmosphere, and fills the pods with nitrogen, which then get flown to Mars. And rotating skyhooks, often called rotovators in this context, can still work on Venus since it does have some magnetic field and there's abundant solar power to use. And there are other ways to regenerate momentum for a skyhook as well. But since there is, it might be easier just to use floating mass drivers. When it comes to floating structures, ones being held up the same as a blimp, a thing to remember is that they can be very big, and that top can be higher than the bottom. So you could build a mass driver where the refineries are at, and the launch points are lower down where the air is thicker, while the exit point and solar panels running it are up higher where there's less air to cause drag on the projectile and attenuate sunlight. We'll look at Venus in a bit more detail in a moment, but I want to give a quick mention to wormholes. Wormholes are obviously another way to move mass fast, same as artificial gravity is a great way to adjust a planet's gravity to Earth normal, and nuclear fusion is a great source of cheap and abundant power. Of the three on that list, only the last one, nuclear fusion, appears to have any real chance to appear in the near future for us. And personally, I don't hold up much hope we'll ever have the other two, wormholes or artificial gravity. This video is about all the options though, so it wouldn't be right to skip mentioning them. Fusion is quite likely to be available for us to help in terraforming, and it will help a lot, but we'll try in this video to address options without using it as well. Ditto, nanotechnology or genetically engineered organisms able to eat rock and spit out gas on an otherwise airless world would be very helpful too. But none of these things allow super rapid terraforming because of thermodynamics. As we discussed when we were talking about nanomachines and gray goo in the Fermi Paradox Apocalypse How video, every mechanical process, or chemical electrical process, generates heat. When you start running the numbers on this stuff, you'll find that planetary transformations like terraforming usually generate way more heat regardless of the method than the planet gets in several years of Earth-like sunlight. So you can't go too fast, or you'll melt everything, including your machines, in the excess heat. Even with things like wormholes, you have to consider how all that mass transfer is going to affect pressure and heat. We still won't look at these options much though, because not only are they outside the realm of the near future, but they also make the subject pretty boring. If you can dump a vial of nanomachines on a planet and just come back to it ready-made in a couple of decades, there's not much to discuss. Similarly, if you've got functioning wormholes, then you can not only open them to places with abundant water or air, and open them to places with pre-existing industry to make transport of people and infrastructure easy, but you could also open them near or maybe even in your own sun, which is obviously a pretty handy way to get more light on Mars or more hydrogen on Venus, and would give you a power source at least on par with nuclear fusion. Also, while discussing nuclear fusion, I'd be remiss if I didn't mention the one working form of nuclear fusion we currently have, and its application for terraforming. Thermonuclear bombs, or fusion bombs, have a long history with terraforming contemplations. You can use them to blow off the excess air on a planet, or rapidly cook air out of planet soil. Needless to say, you've got a fallout issue, but bigger bombs generate almost all their energy from fusion, which isn't a big radioactive fallout generator anyway. A lot of people flinch away from terraforming Mars by starting with nuclear bombardment, bombardment that would eclipse the worst Cold War scenarios, but it is a lot more manageable than you might think of in terms of irradiating a planet beyond habitability. Truth be told, it gets a lot of mention in terraforming conversations, exactly because it is such a good approach in spite of the radiation issue, as there's really just no such thing as non-destructive terraforming. That's why such a bioforming versus terraforming ethics debate exists. Let's get back to Venus. Often overlooked in favor of Mars, it's easy to forget that Venus has a lot more going for it in some areas. Its gravity is nearly the same as Earth's, it's got plenty of nitrogen, and it's got plenty of light. Those last two are actually the big problem. Venus is very hot and its atmosphere is nearly 100 times more massive than Earth's, and it's mostly carbon dioxide, which is heavier than nitrogen and oxygen air. Short term, in the paraterraforming sense, that atmosphere is so thick you can float normal air in it. Conveniently, in the upper atmosphere of Venus, by the time the pressure drops to Earth normal, the temperature also drops to something comfortable too. At about 200 miles up, you can float a balloon made of normal human breathable air at a normal human temperature and pressure, and still have lifting power since it's less dense than carbon dioxide. Now that needs to be in a metal shell and support some weight, but if you're not clear on how lifting power of gases works, it's pretty straightforward. You just take a given volume of your local air and figure out its mass for that pressure and temperature, then subtract the mass of an equal volume of your lifting gas at the same pressure and temperature, or at a higher temperature for a hot air balloon, for instance. Whatever mass is left over is the mass you have to work with for your shell holding the gas inside and for your payload. The advantage of using normal air is that you can use the entire volume of your object instead of attaching something separate like you need to do with helium, and you'd also have a reserve of breathable air. If you're curious, for air and carbon dioxide, that difference is about 700 grams a cubic meter, or about 44 pounds for a 10 foot by 10 foot by 10 foot cube of 1,000 cubic feet. So if you made an aluminum balloon, for instance, 200 meters in diameter, that gives you a volume about 4.2 million cubic meters, or about 3 million kilograms or 3,000 tons of lifting force. It also means your shell is about 125,000 square meters, and a millimeter thick sheet of aluminum weighs just under 3 kilograms per square meter. So if you're willing to devote half of your lifting mass to making that shell, it would be about 4 to 5 millimeters, or about a fifth of an inch thick. Now if you double that diameter, you get 8 times the volume and lifting force, but only increase the surface area by a factor of 4. So you can get double the thickness on your shell, or use the same thickness, but only need to use a quarter of your payload to be that shell, not half. And that keeps going up, as volume always rises faster than the surface area. So you can make some fairly impressive floating structures on Venus, especially if you're bringing in hydrogen, which has an even more lifting power there. You could have whole floating continents, like tied together rafts. This doesn't work as well on gas giants because they are made of hydrogen and helium, so your breathing air has to be part of your payload, not your lifting gas, which would probably need to be hot, pure hydrogen to even be a little bit feasible. And hot, pure hydrogen is not necessarily a good thing to keep around in large quantities. But it works on Venus, and worlds like Venus, just fine. Problem is, what next? Well, there doesn't need to be a next necessarily. Same as you could just dome over Mars as a world house, you could swath all Venus in floating cities, and even if you took all the nitrogen away to use on other worlds, you'd actually float a little bit better since it would make the air outside your balloons a little bit denser by removing it. But if you want to live on the surface and slowly remove the super dense atmosphere, you're going to eventually need to transition from those floating habitats, and that would probably mean supporting them from underneath with pylons. For Venus, those would need to be a couple 100 miles high. If you saw the video on mass drivers and launch loops, you might recall at the end we discussed space fountains, giant thin structures that can be built to heights far beyond what normal building materials allow. These would be an example of how you could keep holding those habitats up while you made Venus's atmosphere thinner and cooler. But how would we do that? Well, one option is just to transport it away bit by bit. Another option for cooling the planet is to erect giant solar shades between Venus and the Sun. At the kind of pressures Venus's atmosphere has, by the time it hits about Earth temperatures, the carbon dioxide will reach its supercritical point and start falling down and forming seas of carbon dioxide. It's only at Earth pressures that carbon dioxide has no liquid phase, going straight from dry ice to gas. At pressures 5 times higher than Earth, it forms a liquid, and Venus's pressure is 90 times Earth's, not just 5. So you get seas and oceans of carbon dioxide. You can just keep shading the planet then, dropping its temperature below Earth's by not letting much or any sunlight in. Soon it will drop to temperatures too cold for life. At 217 Kelvin, or negative 70 degrees Fahrenheit, those oceans will freeze into dry ice. And you just pave over them. When Paul Borch ran the calculations on this cooling time, it worked out to be only a couple hundred years. You could speed even that up by erecting cooling towers rising from the lowest to hottest places on the planet. So for instance, all floating cities could wait till the atmosphere cooled enough near the ground to build towers, space fountains to hold them up, and use those to pump heat off Venus faster. While you're cooling the planet, you steal nitrogen from the air and bring in water or hydrogen to make water. In a couple hundred years, you pave over the dry ice, frozen oceans and seas, and then remove some but not all of your solar shades to bring the temperature back up to Earth normal. The 1991 paper by the late Paul Borch, titled Terraforming Venus Quickly, goes into more details on floating cities, atmosphere cooling, solar shades, and the works. It's fairly short, and Borch had a knack for putting in all the technical details while still making the papers readable without understanding those, so I do recommend it, and it is linked below. Now, giving Venus a day as long as Earth's is another matter, and we're going to come back to that later. First, I want to briefly talk about the opposite case, places where there isn't enough air, like Mars or our own moon. I mentioned earlier that people tend to mistakenly assume these places are too small to hold an atmosphere. There's some truth to that, but not the way they think. Air, depending on what it's made of and how hot it is, has a speed associated to it. That speed, essentially the average speed of gas molecules for a given mass and temperature, is called the root mean square speed. The equation I've got up shows you how to calculate that, and this table shows you what that is for various common gases at roughly Earth temperatures. Take a moment to note that the temperature is in Kelvin, and the speed rises with its square root. So if you want to double the speed, you need to quadruple the temperatures. We live at around 300 Kelvin, quadruple that is 1200 Kelvin, which is even hotter than Venus or Mercury. But even doubled, most of these would still have a speed fall short of the escape velocity from even a place like the Moon, where the escape velocity is just over a fifth of Earth's. Now, not all particles will be moving at the same speed. Some will move faster, following a Boltzmann distribution curve, and this is called the Jeans escape mechanism. A very small fraction of gases will be moving much faster. At any given time, about a millionth of them will be moving 4 times faster than normal. Meaning for Earth, free hydrogen and helium gases will occasionally be moving at sufficient speeds to leave. Earth loses an estimated 100,000 tons of gas a year this way. Almost all of it is hydrogen and helium. If a planet is cooler, like Mars, it would lose less. And if it's got a lower escape velocity, like Mars, it would lose more. But as huge as 100,000 tons a year sounds like, Earth's atmosphere masses about 50 billion times that. Even places like Mars or our Moon would take geological timescales to shed an atmosphere via Jeans escape. But that's not the only way to lose air. We know of 2 others. Planets can leach air into rock and dirt, called sequestration. It can also lose it to being blown off by nukes, and of course comet and asteroid impacts can do the same. Another way, a bigger way, is for the individual particles to be hit by radiation and slammed clean free of the atmosphere. If you picture a helium atom kicking around the thin upper atmosphere of a planet, that then gets hit by a powerful photon like a gamma or X-ray particle, it just soaked up that photon's entire momentum. If we're looking at the helium atom on the terminator of a planet spinning away from the Sun, then it's got some additional momentum already from the planet's spin. Same as we launch rockets west to east to take advantage of the Earth's own spin to get into orbit. If that helium atom is already moving in that direction, as many will be, and has the planet's own spin, and gets hit by photons which are also moving in that direction, the combined energy and momentum can send it zipping off into space. This is generally going to throw off far more atmosphere than Jeans escape. This is also why you hear about the importance of magnetospheres to making planets habitable. It's not just the radiation off the Sun, before it's been filtered by our own air and magnetosphere, that is inimical to life. It's that without a magnetosphere to help counter the highest energy particles, you'd have more air particles getting launched away. And magnetospheres can also deflect charged particles, like lone hydrogen, nitrogen, or oxygen atoms, back down into the atmosphere. There's more to it than that. For instance, Venus has a very dense atmosphere in spite of being way hotter than Earth and having no appreciable magnetosphere. But that's all the more time we can spend on it today. Some way form, any planet or moon massive enough that its escape velocity is a couple thousand meters a second can hold an atmosphere for a very long time by human standards. so long as you shield the planet from high-energy particles and radiation. You do that with a magnetosphere, though there are other ways we'll also discuss. Now, you'll occasionally hear people suggest you get Mars' core spinning again to produce sufficient magnetosphere, and that is possible, but it is way harder than just dumping a nuke down a very long shaft. If you've seen the movie The Core, where the Earth's core stops spinning and they travel down to get it started again, then just ignore every single thing in that film mentioned as science. Honestly, I've seen better science in some of these old 1950s sci-fi series like Commander Cody, where they walk around on the moon without spacesuits or take off in rockets with rolling chairs in them. Moving on. You can, of course, dump millions of nukes off to reheat and respin a planet's core. You wouldn't want to be on the planet while this was happening, though, since things tend to expand when heated, and the kinds of earthquakes that would set off would make a major earthquake on Earth seem like a light ground tremor, and they'd probably go on like that for centuries. So you'd probably go the artificial route instead. You can make a magnetosphere by doing rings of solar-powered satellites around a planet generating magnetic fields. This is a lot more power and energy efficient than melting millions of trillions of tons of iron and nickel in a planet's core. Similarly, just like with solar shades, you can stick magnetic deflectors out of the planet's L1 Lagrange point with its sun and deflect the solar wind away. The other option is to just use straight matter to stop the radiation. Same as you can stick thick domes overhead on a planet to cut it down, you could litter the planet's orbit with many concentric layers of thin material, or do the same at the Lagrange point. All of these approaches need maintenance too, parts replaced, but they'd be a tiny fraction of the mass of a planet core, and a lot of planets would already have various small moons in orbit that could be pulverized carefully to generate such a shield. Superconducting magnets are a lot easier to keep working in space in many respects, so as they hopefully get better and cheaper with time, an artificial magnetosphere becomes a lot saner as an option. We're already looking at this as a protective system, like in the tethered mag shield design for interplanetary spacecraft to get both their radiation protection and some artificial spin gravity at the same time. If you saw the video on orbital rings, then you already know the idea of a giant superconducting ring around a planet is pretty feasible, at least a lot more feasible than reheating a planet core, and also lets us do it for places like our own moon that couldn't realistically produce enough on their own anyway. It's also good for options like Venus, where the day is so long that you don't have much of a magnetosphere, even though the entire planet is molten, not just the core. Same issue for terraforming Mercury. Yes, it's really close to the Sun, yes, it's even less massive than Mars, yes, its day is a couple months long, and yes, it could be terraformed too. Solar shades, artificial magnetosphere, solar mirrors to bounce light around so night and day doesn't last months. Paraterraforming on a place like Mercury isn't terribly bad either. If you want to build a base on Mercury where there's no air to transfer heat, you stick your base up on stilts or sturdy materials that don't conduct heat well, and you stick a shiny metal umbrella over it to shade it. I sometimes call this a mushroom habitat. Mercury's surface gravity is about the same as Mars has, almost identical, because while Mercury is smaller than Mars, it's also denser. It's denser because almost all the light elements have baked away, so you can't expect to get your water and air locally. Now, we don't really know if Mars and Mercury's surface gravity is really enough for people in the long term. It probably is, but as I've mentioned in the past, you could build your bases there to spin, and thus combine natural and spin gravity to get something more comfortable. If you're already built up on stilts and under an umbrella, spinning a base through a near non-existent atmosphere just isn't that big of a deal. You could forego that setup by just placing solar shades in orbit at the Lagrange points too, and give the planet a few decades to chill out. Most solar system expansion ideas usually call for Mercury to be mined out till there's nothing left to make artificial habitats out of, so I don't usually spend much time thinking about terraforming the place. But even then, you need thousands of years minimum to rip the place apart, so bases on stilts under mushrooms makes a lot of sense. If you're using the planet's own sunlight to extract its minerals for off-world export, then even with maximum efficiency, you're talking timelines of many thousands of years to do that even for a place like Mercury, which has far less gravity and mass than Earth, and far more sunlight than Earth to power the process. We've mentioned daylight too. Most planets don't have day lengths we'd find comfortable. Mars has a day very similar to Earth's own, but Venus and Mercury definitely don't. And most large moons like Ganymede or Europa or our own moon take many days or even weeks to complete one day for themselves. We talked about the example of moons with Earth-like days in the third video in our Habitable Planet series, but most moons don't have one-day orbits and don't have Earth-like mass. So what do you do to get a 24-hour day if the planet doesn't have one? We mentioned meals, and it's possible to use a combination of orbital meals and shades to produce an artificial 24-hour day on a planet, in terms of its night and day length, not its actual spin. This gets pretty muscular and complicated, but it's nothing like as muscular as changing a planet's rate of spin. Still, it can be done. You can change a planet's spin without needing any super science. This isn't easy, but it's not any harder, in some ways easier, than trying to screw with a planet's core to make a magnetosphere. If the planet is spinning too fast, as many would be, Earth's day used to be 12 hours long after all, you can actually harvest that energy to power your terraforming while slowing the planet. Earth's current rotational energy is about 2 times 10 to the 29th joules of energy, which is a lot of juice. For comparison, it's equal to all the energy that sun shines on Earth for 1 trillion seconds, or about 30 years. This also tells you how long you need to power something like that strictly off solar power, or how long you need to spend to avoid dumping so much energy on a planet you'd melt the place. The energy involved doing this is fairly comparable to what you'd need to spend to get a planet's core spinning to generate a decent magnetosphere. How would you do it? Well, you could attach rocket thrusters right to a planet or detonate millions of nukes, but a better route would be to build giant towers over the planet's atmosphere and point orbital mills at them like a big water mill. Or aim those same mills at one edge of the planet and use that energy to bake air out of the soil while you're at it. This is going to take a long while, but that's okay because increasing the spin rate of a planet should be done slowly to give the stuff a chance to settle down. Slowing it down, same concept, but you could potentially power things with that. A planet's spin isn't the easiest thing to tap for energy, but waste not, want not. Same concept for adjusting a year, except if you want to adjust a planet's year, you're also changing the sunlight it gets. Only thing is, Earth's orbital energy around the Sun is about 10,000 times its rotational energy around its own axis. Even ignoring the energy issue, or how to get that much energy, it's hard to do this in a non-destructive way in less than many millions of years. You normally use a gravitational tractor, which is where you stick something, like our own moon, in orbit around a planet and shove that object away from the planet when it's on the far side of the Sun, then back toward the planet when it's near the Sun. That keeps the object in the same relative position to the planet while pushing the planet further away from the Sun. Do the reverse to bring the planet closer. You could do this with a giant solar sail being hit by sunlight, or many of them, but you can't make them too thin or dump too much energy on them at a time or they'll fly off. This is a lot like the Shikata thruster I've discussed before in the megastructures or Dyson Dilemma videos as a way of moving entire suns. Moving planets, moving stars, moving whole galaxies, it isn't the realm of super science, it's just the realm of brute force. It's the difference between stacking a few stones across a creek to make a small pool one afternoon and building the Great Wall of China. Same process, just way more time and effort. The key thing to remember is that even if you have an infinite power source, you can't move a planet too fast without heating the planet up. Your average planet's orbital energy tends to be on a similar scale to what you need to vaporize a planet, so you can't be applying this all at once. The other aspect is that since it's similar to the energy needed to vaporize the planet, someone's going to point out that it makes way more sense to just convert the entire planet into trillions of orbital habitats, with millions of times the planet's living area. Earth's rotational energy is comparable to the sunlight it receives over 30 years. Its orbital energy is more like 500,000 years. Energy used in such processes is going to see a big chunk disappear as heat, so if you don't want to roast the planet, you need to go very slow, even if you have the energy to go faster. Needless to say, it's always going to be both faster and easier to use orbital mirrors or shades to replicate the effect, so moving planets is probably the sort of thing you'd only ever do with a planet to move it away from its own star as it heats up over its lifetime. Stars get hotter as time progresses and eventually become red giants. You can take billions of years to do that, and would want to anyway, slowly moving a planet further away as its star gets hotter. Now, axial tilt can be adjusted in a similar fashion, but it's more like adjusting day length than year length. Same sort of concept. Use gravitational attractors or various other means. Takes time, it's very brute force, but it can be done. Gravity is harder. If you don't like a planet's gravity, you can only add or remove mass. If the gravity is lower than Earth's, you can make spinning habitats that combine natural and spin gravity. If the gravity is higher, the only way to do that is to hang some material like ultra-dense deuterium or neutronium over your city to locally negate some of the gravity. This isn't necessarily completely undoable, but people might feel a little nervous living under billions of tons of matter hanging over their heads. On the other hand, if you live in the lower floor of a skyscraper, you live with thousands of tons of matter hanging over your head anyway, and 1,000, 1,000,000, or 1,000,000,000,000 tons, you're basically just as dead if it falls down. Gravity is also very hard to bioform around, because while low gravity would likely not be a big issue, high gravity is. Slip and fall in the shower on a high gravity board and you'd shatter every bone in your body. We discussed in Launch Loops and Mass Driver video how the big limitation on mass drivers launching people is that we just can't handle the high acceleration. Acceleration is the same as gravity according to Einstein. So borrowing someone inventing the cool artificial gravity most sci-fi TV shows have, because it's hard to film in zero gravity, worlds with much higher gravity than Earth aren't good for terraforming. And even for paraterraforming, unless you're cool with transferring your mind into a cyborg body with titanium bones. Which, to be fair, a lot of us would be fine with, especially the generally pro-science sorts who probably make up the majority of my audience. But I usually try to focus on the routes that don't involve cyborging people up or tinkering a lot with their genes, even though I'm basically a transhumanist or extropian myself. Key thing, if you get a way of generating or negating gravity, same as if you get wormholes or perpetual motion machines, the entire landscape changes so much I don't see much point in analyzing it. Same as in my Dyson Dilemma video, where I mentioned we might find a way to open portals to uninhabited parallel Earths, and if we did, you can pretty much write off any space exploration, and not done specifically for scientific research or because we can prestige efforts like climbing Mount Everest. We climbed that mountain many a time, nobody's ever built a city up there. Now, we've looked at a lot of terraforming notions, but we haven't even scratched the surface. I may come back and do some more videos on this subject in the future if people seem interested, and I'll continue to mention planet-specific options in the Habitable Planet series, but for more information, take a peek at some of the links below and videos I've attached. We'll be looking at alternatives to terraforming in the form of building worlds and megastructures in the Megastructure series. I can't give you any good links on bioforming, I'm not qualified to evaluate the biology and genetic engineering, but if you happen to be, feel free to leave some comments and links below. Next in the video series, we'll be taking a look at rogue planets in the interstellar void, where terraforming can only be done with artificial power sources like fusion, and then doing another standalone video discussing early interstellar colonization concepts like we did with the interplanetary colonization here. After that, we'll be diving into rotating habitats as an alternative to terraforming. If you've enjoyed this video, which I assume you have if you've made it this far, make sure to subscribe to the channel and like the video, and try out some of my other videos as well. As always, thanks for watching, and have a great day.